Hello, this is Dr. Muhammad, and this is another video under dynamics of structures. Still, we are under multi-degree of freedom systems, and today we are going to talk about the orthogonality condition, and after that I'm going to talk about the normalization of mode shapes, and then I'm going to take an example, work out an example regarding normalization of mode shapes. Okay, so now for the orthogonality of modes or of mode shapes, we are going to talk about this property because it is important property that we need to understand for specific reason, for the case where that we are going to solve the multi-degree freedom system dynamically. So this property, which is I'm going to explain or start to explain it in today's video, this property is important because it will be used in solving dynamic problems of multi-degree freedom system. Why I'm placing emphasis on this point, because after going into the mathematics of this orthogonality condition, sometimes you are asking yourself why we are studying this condition, or why we go into this math for proving this this condition. The main idea is it would help us in dynamic problem solving for the multi-degree freedom system when we are going to use a specific procedure called modal superposition method. Modal superposition method. So this is the main reason for why that we are going to use this orthogonality condition, and I'm going to tell you in specific or in particularly why we need to understand it and why we want to prove this condition. Okay, but later on when we are going toward the end of the proof. Okay, now what should we, or what we want to do from this orthogonality of modes? That we want to prove the following, okay? The following, which is for any mode shape, AM transpose, and this is a vector, times the mass matrix, which is, this is the matrix, diagonal matrix, because we are talking about masses, times the mode shape, but this mode shape is different than this one. So this is what we call it AN here, and this is AM. So consider it like mode shape 1, for example, and mode shape 2 for a system that is having 2 degrees of freedom. Okay, so we want to prove that AM transpose times M times AN equals to 0. This is vector, this is matrix equal to 0. With one condition, that the frequency of the mode shape M does not equal to the frequency of the mode shape N. Okay, this is the major, or this is the condition for us here. Okay, so first of all, we need to think about this from the mathematical point of view. Okay, this is number one. And number two, we are going into the significance of this, physical meaning of this. Okay, but later on. Now we want to go through math, how we are going to prove this, and then we are going to understand the physical or the significance of what we are talking about. Okay, and with this condition as well, with this condition, so we are having, so with this condition, we are having another important condition that is commonly used also, which is related to the stiffness matrix in this case, which is K. We want to prove that AM, in the same sense, AM transpose, I forgot to put here, this is the transpose times the mass, or times the stiffness matrix, equals to, or times AN, the vector of another mode. As we said, assume this is mode 1, for example, this is mode 2, equal to 0, for the same condition, that is omega M does not equal to omega N. What is the meaning of omega n and omega m and n? This is the frequency based on which, the circular frequency based on which the first mode, or this mode, which is mode m, is going to vibrate. And omega n, the same, it is the circular frequency based on which this nth mode is going to vibrate. It is dynamically called the circular frequency. Mathematically, we call it eigenvalue. So it is like we have like two faces of the coin, mathematics and dynamics. So here we understand the meaning of this frequency from the mathematical and from the physical, or the significance of it. Okay, so the question is, well, what does this kind of thing, or this condition is going to, how it is going to help us in the modal superposition method? Actually, if you look here, if we have a multi-degree freedom system that is consisting of many degrees of freedom, this vector and this vector is going to be very huge, and this mass matrix and stiffness matrix are going to be very huge as well. So it is a computational burden. Vector times matrix times another vector, we found that it is going to be like very large computational effort here. All of a sudden we found that if we could see these terms, or these items, the vectors and the masses, in this way arranged during the superposition or modal superposition, directly we are going to substitute it with 0. This is the idea here. So we are going to have in very huge and complicated systems, we are going to face multi-degree freedom systems. Then whenever we can see these, or this arrangement of the modal or mode shapes and the mass matrix, or the mode shapes here and the stiffness matrix, then we can simply put it as 0. And actually, when you are going to work with, as we are going to see later, that for modal superposition we are going to find this arrangement of vectors and masses or matrices are going to be frequently encountered. This means that knowing something like this from the mathematical standpoint going to save us a great deal of computational effort. Okay, so that's from the mathematical point of view, and this is why we need it in the dynamic analysis solving approach for our modal superposition method. Okay, now let's erase this and go further. Okay, as we can see, the product of these items equal to 0. Let's talk about this. So here the product of these items equal to 0. This means that we are equals to 0. This greatly simplifies manipulation of equations in the modal superposition method, as I said. And this is the main hint that we need to keep in our mind. These terms are frequently encountered, and whenever we can see, or whenever we encounter it, we can put it 0. This means that a great deal of simplification is going to be there. A great deal of simplification is going to be there. Okay, now let's go to the proof itself and see how we can go with it. So first of all, we want to recall that from previous lecture the following equation. So we need to recall this equation. Do you remember this equation? It was equation 3, that based on which we were putting the stiffness matrix minus omega squared times the mass matrix times the vector of the mode shape that we are, or the mode shape, and this left hand side is going to equal 0. The left hand side, it is a matrix here between the blue parentheses times the vector A equals to the vector of zeros. This is, we have proved it in the last video, in the last lecture, and you can recall this from where we got this equation. Okay, and then we are going to simply rearrange this equation in a way that is going to be easy for us to prove our main orthogonality condition. So we're going to rearrange the right hand side and the left hand side of this equation. Okay, so we are going to rearrange it. So in this way, if you look here, we're going to find k, it is going to be multiplied by a, which is the vector of any, let's assume it is for n mode, for nth mode. So k from inside the blue parenthesis going to be multiplied by this vector, stiffness matrix, times a n, the vector of mode or the nth mode shape, equals to the right hand side is going to be omega squared times m, the mass matrix. It's going to be on the right hand side after being multiplied by the nth mode shape a, which is, we're going to call it an. So based on this, this is applies for the nth mode, means this equation applies for any nth mode. The stiffness matrix times the modal amplitude or the mode shape of this mode equals to the circular frequency of this particular mode shape times its mass matrix or the mass matrix of the system times the vector of mode, this vector or the mode shape itself. Okay, so this is how we can understand this this equation, okay, after rearranging. Okay, now let's go to the next part, which is related to this equation. If we're going to look to it again, and we need to understand it in a physical sense so that we can give an interpretation for the equation in a better way. As I said many times, we need to be patient regarding the mathematical equation, because sometimes we need to understand the significance of the equation, the left hand side and the right hand side. I mean that sometimes we need to read them in a different way. It's not only math here, not only mathematics or mathematical terms in the left hand side and right hand side and matrices and vectors. Sometimes math is going to provide for us an easy tool to manipulate many variables, but in the same time it sometimes covers the main principle understanding or the important understanding of the significance of the items. So we do not want to lose or let these principles or important understanding to be obscure. Okay, so if we look to the equation again, we can say that we have stiffness matrix multiplied by mode shape, which is amplitude in itself. It is like set of displacements, right? In each degree of freedom, we are going to have a specific amplitude related to this, related to the degree of freedom. So we have, for example, A1, A2, A3, and so on until AN, right? So this is what it is assumed to be like the amplitude, the displacement amplitude, right? And remember well that it is not the absolute one, because we, as we have mentioned before, we have the ratio between the amplitudes. We are maintaining, we can obtain from the equation the ratios only, but the absolute values we cannot do it, we cannot obtain it. So let's assume now that this is the amplitude, even that it is the ratio of others, but let's assume it is the amplitude now, and it is multiplied by stiffness. Okay, whenever that we multiply stiffness by amplitude, okay, or displacement, stiffness times displacement, it equals to what? Force, right? And because we are talking about stiffness term here, so it is logic to say that it is going to be elastic force, elastic force. So the left hand side of this equation is going to be stiffness multiplied by amplitude or displacement, which means physically it is elastic force. Okay, Now let's have a look on the right hand side, which is omega n squared mass matrix times the modal amplitude vector. We're going to arrange it in a little different way, but a little bit different than this way to let us understand. Let's put this M matrix in the beginning here, so it is the mass matrix, and then an after that, and the omega n squared at the end. Okay. If we agree, both of us now, we agree that the left hand side is elastic force. Remember, it is elastic force. Okay. And the right hand side, we arrange it in a way that is one item is giving us mass. So by default, the remaining items should be what? Exactly. It should be acceleration. This must be acceleration. Why? Because if the left hand side is stiffness force, elastic force, this means that we need the right hand side to be force also, a kind of force. We are sure that we have mass term, which is the mass matrix here. This implies that the remaining terms supposedly to represent acceleration, right? Because mass times acceleration, it would be force, which is going to equal the left hand side, the elastic force. Okay. And whenever that we have in our system mass that is going to be multiplied by acceleration, commonly we call this inertia force. Okay, inertia force. And this is logic actually. If you go back to the elastic or the single degree freedom system, we're going to see that in cases where the elastic forces, if we do not have damping, for example, elastic forces, in order to maintain the system in equilibrium, we need the elastic forces to equal the inertia forces, right? So this means that the right hand side must be force as the left hand side. This is elastic force, this is inertia force. Okay, so this is an important issue we need to keep in our mind. I hope that I could bring this understanding clearer to you, but it's really important to understand this item. Okay, so let's highlight something here. So as I said, this inertia term, it is, or the inertia force, this is must be inertia force, as we said. This is inertia force because one term is the mass. That's very true. So the other term should be acceleration. That's right. To have force as in the left hand side, okay, in order to have force as in the left hand side, as in the left hand, when mass is multiplied by acceleration, then we have inertia force. Okay, this is only what we should understand when we are dealing with this equation. Okay, now we have transformed this equation into physical meaning. Okay, we have something now we can understand, which is elastic force here, inertia force here. The stiffness matrix and the amplitude or the displacement vector, it represents something for us now, and the right hand side, it is the same, the mass matrix times these two terms, omega n squared times a and the amplitude, it represents for us acceleration times mass, which is an inertia force. Well, that's very nice. Now let's go to the next step and go smoothly to the next point. Okay. Now I want to highlight something here. Sorry. Okay. Now we need to understand an important concept in order to proceed for the proof of what we have mentioned. Now we need to introduce an important concept, okay, that will help us in the proof. Okay, it is only like a sidetrack concept or law or theorem that is going to bring to us nearer to the physical meaning of the orthogonality condition. This is what we call it Betti's theorem. Okay, and it is for linear systems. Okay, it is for linear systems. I'm going to read what this Betti's Betti's theorem is telling us in the course of our mode shapes and the work done. So it says that the work done, this means that we have work done here, means that there is force times displacement by some way or another, right? So the work done by the mth mode, which is one mode shape. So the work done by the mth mode, inertia force, again inertia force, this means that we know there is mass times acceleration here, okay? On the direction of deflection, okay, so the work done by the mth mode, inertia force, on the direction of the deflection due to the nth mode is equal to the work done by the nth mode, inertia force, on the direction of the deflection due to the mth mode. I'm sure that you didn't understand anything from this, okay? So now you can pause the video and read it again, okay? Read it again. And I think that after reading, you are not going to understand it directly, because it needs to be, I think it needs to be like illustrated by some figure, as I'm going to do, okay? So now we are going to understand the meaning here. Just you are reading something here, and I want you to highlight these things, okay? So we are talking about work done. We're talking about inertia force for mth mode, right? And then we mentioned something in the direction of deflection, okay, of another mode called nth mode, okay? So we have like two parts now. Work done by the inertia force of the mth mode on the direction of deflection of the nth mode is equal to, it is equal to the opposite of what I have said, to the work done, the same again, work done again, by the nth mode, inertia force, still we are talking about inertia, on the direction of the deflection due to the mth mode, okay? So these are the keywords here. These keywords, we are going to understand them more by giving this simple illustration here. Assume that we have mode N and mode M. So we have N and M here, and we are having, let's assume that mode M here, it is, as you can see here, it is displaced with D1 and D2, and the degree of freedom 1 and degree of freedom 2. And the forces that is going to displace this mass by D1 and D2 are going to be F1 and F2 respectively. And if we look to the mode N, you're going to find, let's assume it is the second mode shape, for example. If you keep in your mind the previous example of the previous video, then you're going to find that this mass is going to, let's assume it is going to the left direction with amplitude of displacement D3, and this is due to a induced force or inertia force F3, and degree of freedom 2, it is going to move in this direction, right direction, with D4 due to inertia force induced here F4. What I have mentioned in the Betti's theorem or Betti's law here, it is interpreted by this simple equation. So the point is, take care that the forces, I put it in the red color. So whenever I want to say there is work done, I'm going to say that the work done here for the mode M, for example, okay, it is supposedly to be F1 times D1 plus F2 times D2, for example, right? This is the work done here. But Betti's theorem or concept is telling us something else, telling us that these forces, F1 and F2 of this mode, okay, if we multiply them by the displacement D3 and D4 respectively, they are going to equal the product of F3 times D1 plus F4 times D2. So let's repeat it again. Okay, so F1 times D3 here plus F2, this is F2, times D4, this is D4, equals to F3, which is the inertia force here, times D1, which is the displacement here of this mode, plus F4 times D2. Okay, do you understand this? The color code here would help you understand where are the forces that we're talking about. F1 and F2 related to mode M, F3 and F4 related to mode N. D3 and D4, they are related to mode N, and D1 and D2 related to mode M. Okay, so this is the meaning of Bett's theorem. Remember, Will, this applies for linear systems. This applies for linear system. Okay, this is only for linear system. We're talking about linear system. This is one of the physical phenomenon for linear systems. You might not understand well what I have explained up till now, but already we have some similar concept for this in the structure analysis for related to the influence line. If you remember, I'm going to talk about it. Do you remember something called Maxwell's reciprocal theorem? I'm going to talk about it in a minute now, but only for this equation. Remember that this is work done, as I said, by the mth mode inertia force in the direction of the deflection due to nth mode, okay, and is equal to the opposite, which is the work done by the nth mode inertia force on the direction of the deflection due to the mth mode, where that F1, F2, F3, and F4, they are inertia forces. It is the forces that is going to be induced in every mode in order to displace it. And D1, D2, D3, and D4, they are deflection amplitudes. Okay? Okay. If you didn't understand, then it's okay, no problem. You are going to understand maybe from the next slide when I'm going to explain more about Maxwell's reciprocal theorem. We do not need Maxwell reciprocal theorem here, just I'm going to give it because it's like a subset of this Bett's theorem, and it's going to make it maybe more understandable for you. So here, remember that this is, as I said, hint about Maxwell's reciprocal theorem. Okay? So remember, in Maxwell's reciprocal theorem, commonly we take this in the influence line, as far as I can remember, that we can say it is as a subset. It is a subset of Bett's law or Bett's theorem. So if we have a cantilever, as you can see here, this is linear system. Again, we are talking about linear system. Everything here, it is related to linear system, because if we are going into nonlinear, everything is not going to work as we are explaining here. And let's assume that we have 2 points, point 1 and point 2. And we applied on point 2 with load P, and we applied on point 1 with load Q. They are different. And when we apply this load, which is P, we found that the displacement at the point, at this point, point 1, let's assume it d or delta P1. And when we apply this Q on point 1, we found that the displacement that is going to be developed at point 2 is going to be delta Q2. The Maxwell's reciprocal theorem says P times delta Q2, this is the work done, okay, P times delta Q2 equals to Q times delta P1. Okay, this is what we call the Maxwell reciprocal theorem, and it applies, as we said, in structure analysis for influence line. It is pretty similar to Bett's law. We can assume it as a subset of it, okay, because they are similar in understanding. Okay, so it is only for refreshing your memory regarding the influence line and Maxwell's reciprocal theorem. Okay, now let's go back. Okay, now let's go back to the orthogonality condition. Okay, do not lose the main thread that we already have started before. Okay, in this case, we are going to go back again to our mode M and mode N, and we said that we have this equation. We understood now this equation. Okay, we understood this equation mathematically, okay, or physically at least now. As I said, this is the force as long as this system is linear, then this work done here equals to the work done here. Okay, this is physical phenomenon as I said. Then this physical phenomenon, we want to put it in a matrix form, so we need to use math here. Okay, take care of this. We need to use math. Why we need to use math? In order to make it in a form that is easy to be manipulated. That's the main reason for this. So when we put it in a matrix form, we're going to put it like this: F1 and F2 vector, and its transpose times D3 and D4, which is the deflection related to the nth mode. So this is related to mth mode, this is nth mode. Okay, and the right hand side is going to be the same, F3 and F4, related to mode n times D1 and D2, okay, related to mode m. If you multiply this mathematically, it's going to give to you the same equation here that we have put based on Petty's concept. Okay, so this is how it works for us. I want to clean everything here. Remember that here this is related to mth mode, this is nth mode. Here this is related to the F3 and F4, it is nth mode. D1 and D2, it is related to the mth mode. Okay, this is how we put it in this form. Okay, I think that it is clear up till now, and we understand it. Now still we want to go to the orthogonality condition, how we can obtain what we have mentioned in the beginning of the video. Now in a second we are going to understand it. Okay, so now based on that we can say if we have force here times vector, this is transpose, for mode shape m times the amplitude of mode shape n, then it would equal to the inertia force for mode shape n transpose times the forces for, or the inertia forces for the nth mode transpose times the amplitudes for mth mode. What is the meaning of this? Before, as I said, if we go back to what we have explained in the previous slide, we said that we have some force, right, times amplitude, right? And I said this is, for example, was related to m mode, this is related to n mode. It equals to, again, another force and amplitude, and we said that this is related to n mode and this is related to m mode, right? So here I'm going to put it again. This is F. What is F here? The forces that we were talking about, it was the inertia forces, right? That makes the mode or the masses to go in this direction. It is the inertia forces, right? So we have the F1 and F2, right? These are the forces that is being induced. This is the inertia forces. So we can say that the first vector here, it is the inertia force of the mode m transpose. Okay, let's clear it here. So this is the inertia forces. I stands for inertia. So inertia forces from the mth mode transpose times this vector, it is the amplitudes of nth mode, equals to the same, but we are going to flip n and m here. So the inertia forces coming from the nth mode, inertia forces from the nth mode times, remember that is transpose, times this vector, which is the amplitude, the vector of amplitudes of the mth mode. Okay, that's very well, and we understand it well. This inertia force, it equals what? This inertia force equals what? If you go back to the previous slides, you're going to find that it equals to exactly omega m squared times, this is This is because we have transpose here. Let me clear everything. So here we have transpose, right? So it equals to omega m squared times m. This is the vector transpose. So we are maintaining the same transpose here. M times am, right? Mass matrix times the amplitude, right? Times the omega squared. This is what we have said before. It is what? It is inertia force, right? We have mentioned about this before. Let me go back here to make it clearer for you. So here, do you remember, I think before this? Yes, here. And we mentioned here that we have, this is the part here, yes, this is the inertia force. Do you remember we said that? We just rearranged it. Omega squared m times an. We proved this omega squared n at the end here, and we said that this is going to be inertia forces. Okay, we said that it's masses times acceleration, then we're going to have inertia forces, right? That's the contribution, or this is the meaning, the physical meaning of the inertia force, right? So now we can say this inertia force that we were, this term here, it is F(I) n, for example. Okay, it is the inertia force vector for nth mode. Okay, that's what we have explained, or this is what we have already explained before. Let's erase this and go to our main. Yes, now we are here. So this means that the inertia force of the mode m, it is going to be, we are going to put it in this form, omega m squared times the mass matrix times the mth mode shape. And then between these brackets, or between the parentheses here, the curly parentheses here, we are having transpose. Why? Because already we mentioned about this. This is the transpose here. Okay. Similarly, this is the amplitude of nth mode. We put it here. Remember that omega squared m, it is scalar value, and this the mass times the vector here, it is vector transpose, right? And after that we are going to have vector transpose times another vector here. So it is going to be, let's clean everything here, make it a little bit, yes. So now this is vector transpose times vector. This is another vector, right? So we're going to find that this vector transpose times vector, it is going to give us scalar value. So scalar times scalar, it is going to be scalar value, right? Similar, in the right hand side, we're going to apply the same technique. We have omega squared, but it's for mode n. For mode n, this is scalar, and the mass matrix times the vector of mode shape for the nth mode transpose. It is vector response, and here this is another vector. Both of them, they are going to be multiplied, and we are going to have the scalar value. Scalar times scalar, we're going to have scalar value. So all of these matrices are going to be like crushing one another, and we at the end we're going to obtain scalar value. The value on the left hand side should equal to the value on the right hand side. Okay? Okay. Now remember well, this is something that we want to remember. When we are talking about these transpose here, we have the transpose here. So we have matrix times vector transpose. All of them, they are transpose. Remember that whenever we have like matrix times another matrix or another vector, for example, all of them, they are transpose. It equals to this term, or this matrix transpose times this matrix transpose, right? It is simple matrices forms, okay, or operations. And whenever that we have a diagonal matrix like the mass matrix and it is transpose, it equals to the diagonal matrix itself. Okay, so because why this is because it is diagonal matrix. The of diagonal elements, all of them are zeros, so we are having diagonal matrix here. So M transpose equal to M. Okay, they are the same. Well, let's clean and go next step here. That's very nice, I think, for you to understand what we are talking about now. Now we are going to put what we have explained before. So we're going to put AM transpose. So we're going to flip, and the mass matrix is supposed to be transposed, but it doesn't matter here, okay, because it is, as I said, it is diagonal matrix times AN. So we didn't do anything, just we removed the curly braces here, and it was T here, and then we removed them, and we put AM transpose times mass matrix. It's clear here. Times AN, it is from the beginning, it is as it is. Similarly, we are going to make the same for the right hand side. So AN transpose times mass matrix times AM. Okay, and if you look here, we're going to find that these two terms here, I claim that they are identical. They are identical. They are the same. If you look here, you're going to tell me that, well, this is AM transpose here times mass matrix times AN. It is different than AN transpose times M times AM. It is different here. This is different and this is different. So we need to, we might have different values, but they are not. They are identical. How? So let's check the first term to check that they are identical. Let's check the first term here. So in the first term here, let's assume this is AM. AM means that it is, we have like A1, for example, A2, and so on, right? And here this is going to be M1, right, and M2, and so on, right? And then here, but this is transpose, right? Here this is AN, so we have like A1. We're talking about M here, so this is for M, and here A2, something like this for N. The first term here is going to be A1 times M1 times A1 from the N. So it is going to be like this. A1 from the mth mode times M1, the mass of the first mode, times A1N, which is the amplitude of the nth mode, plus blah blah blah, the remaining. You can decompose these, okay? So only I'm going to check the first term because I want to let you know that they are going to be the same. Okay, this is the first term here for the left hand side, and for the right hand side, if you go here, the first term, you can do it by yourself. You're going to find that it is A1N times M1 times A1M. Can you look to this? A1M, M1, A1N. They are the same, just we are flipping this here and here, but they are multiplied. So there is a multiplication here. Okay, it is commutative, so no problem. We are going to have this multiplication or dot product of these vectors and matrices are going to be the same. Okay, so this is going to be the same. Well, what I want to go through here, we proved now this term is going to be the same as this term. Well, this means that we can put it in another form. Okay, so based on that, we are going to say that this term, left hand side, equals to the right hand side term. Okay, 100% sure of this. This means that we are going to take, if we are going to look to the original equation, if we are going to take putting omega, this omega n squared and omega m squared, we are going to put them in the left hand side, and we are going to take them as, take this term here, okay, this term and this term, they are common term, right? So we can take it as a common term, and we are going to put the left hand side on right hand side and rearrange them to make the right hand side to be 0. Okay, so let's go and make this. Here we are going to take exactly, so we're going to have omega m squared minus omega n squared. This This is the term after taking this common factor to be the common factor here, okay? And the right hand side we're going to leave it 0. So this term, okay, this term must equal to 0. If we have two terms here, one term is the difference between the omega m squared minus omega n squared times this term equal to 0. Which term that should equal to 0 from your own point of view? Okay, if I were you, I'm going to claim that this term must not equal to 0, because if omega m equal to omega n, this means that we are talking about the same mode shape. Okay, because they are going to be equal, and it won't happen. Mathematically, it won't happen, because in the eigen problem we have eigenvalue that is going to be associated with eigenvector. So we cannot find two eigenvalues to be identical. It's mathematically cannot happen, right? So this pushes us to the right assumption, which is this factor between this parentheses must equal to 0. And we ended up with this AM transpose times the matrix M times AN. Remember that we have M mode here times N mode here equal to 0. So we're talking about two different modes. So this makes us give this condition that take care the circular frequency of the nth mode is different than the circular frequency of the mth mode. Okay, they are different here, and from here we can obtain the meaning of the orthogonality condition. We can obtain the meaning of the orthogonality condition. Okay, so the meaning here is clear for us. The orthogonality condition between any two mode shapes AM and AN with respect to diagonal mass matrix M. So this is what we call it, the orthogonality condition. The orthogonality condition. I hope that you can understand it now, because after this mathematical manipulation, I hope we have an idea about the meaning of orthogonality from the mathematical point of view. Okay. Again, I recall what I have said in the beginning, that orthogonality condition is important for the solution of the dynamic problem for the multi-degree freedom system using modal superposition method. Okay, and I mentioned about why it is important, because as I said, these vectors and the matrix are going to be multiplied to one another, and the final result for them is going to be 0. So it is going to be very easy for us to manipulate and reduce and simplify the computational effort for the solution of multi-degree freedom systems. Let's assume this to be equation 5 and take care we're going to use it later. Okay, we're going to use it later. So now let's move on and see how we can go through the remaining part. So let's assume that, or not assuming, by pre-multiplying equation 4 by AM, okay, AM transpose. Equation 4, I put it here for convenience. So this is equation 4 that already we have proved before. Stiffness matrix times AN, the vector, equals to omega n squared times M times AN, okay, which is the vector of mode shape for this mode shape N. We're talking about, okay, we're talking about the same mode here. We're talking about one mode, specific mode, which is mode N. So we're going to pre-multiplying, so we're going to put the vector or the mode shape vector of mth mode transpose from both sides. So we didn't do anything, just we're going the same term in the left hand side, we're going to keep it as it is and multiply by the transpose, this vector transpose AM, and we're going to make the same on the right hand side, the same vector transpose multiplied by M and AN. Remember that omega squared n, it's a scalar value, it's the same, so it's no problem to put it here or here, no problem. Okay, just we put it in this term. So I put it in this way so that we can approach to our conclusion. Okay, we can put it in this way so that we can approach to our conclusion. So the conclusion is, again, we are going to have the term, or we are going to draw the final conclusion for us here. So here, as we have mentioned before, this part from the orthogonality condition with respect to the mass matrix, we said that it equals to 0. 0 times omega n squared, it is 0. So the right hand side entirely going to equal to 0. We put it 0. But the left hand side, we left with AM transpose times the stiffness matrix times AN. Remember that we have M mode here and we have N mode here, which is different vectors here. This is transpose, as we said. It equals to 0 as well. Let's clean and go down and write or put the final orthogonality condition with respect to K, the final conclusion for us. The orthogonality condition, we're talking about the orthogonality condition between any two mode shapes, AM and AN, with respect to the stiffness matrix K. So this equation is important equation for us. Why? Because we are having the K here, and this is considered to be another orthogonality condition, but instead of using the mass matrix, we are using exactly the stiffness matrix. Remember that the left or the right hand side here is going to be 0, and remember it must be, we must bear in our mind that omega n does not equal to omega n, and this is something logic, as I said, mathematically before being physically logic. Okay, so I think that by this we are like having now the two different orthogonality conditions in our minds, one related to the mass matrix, which is equation number 5, and this says AM transpose times M matrix times AN equal to 0, and the other one is related to the orthogonality condition between any two mode shapes M and N, for example, but with respect to K, which is related to the stiffness matrix. Okay, so I hope that by this we have like reached the understanding of orthogonality from the physical and from the mathematical standpoint, and I hope that we can pave the road now for the next video, which is related to the normalization. They are going to be, or at least we need to understand now the orthogonality condition, the physical, from the physical standpoint and from the mathematical standpoint. I'm going to recap what I have said in this video because I think it's really important for us. What I said here, that we need the orthogonality condition or the property of orthogonality is going to be important for us for a specific reason, which is related to the dynamic problem solution for multi-degree of freedom system using modal superposition method. Okay, that's it. What is the this orthogonality condition? We have two different conditions. The first one is related with the mass matrix. The other one is related to the stiffness matrix. And both of them, they are dealing with M and N, two different mode shapes, M and N here. The conclusion of this, that whenever we have two modes, they are going to, the dot product that we are going to have here with respect to the mass matrix, going to yield 0. And if we are having the same two different mode shapes, and we are going to have a dot product with the stiffness matrix, we are going to have 0 at the end. Okay, that's the orthogonality condition, and it implies some ideas related to the Betti theorem, as I have mentioned before, And remember that we are talking about linear systems. Bett's theorem is related to linear system, and I have given an illustration here that is giving to you the meaning of Bett's theorem, and it has something to do, or it is related to the Maxwell reciprocal theorem that we know from influence line. After that, I have some manipulation to put the understanding of Bett's concept into the matrix form, and then we realize that we are dealing with some matrices or vectors mathematically, but actually they are having some significance for us. We have inertia forces multiplied by amplitudes, okay, the left hand side and right hand side, and then based on this understanding we substituted with the main equation that already we have obtained before, which is related to omega m squared times mass matrix times am transpose, and we put and substitute in this equation. Finally, after some manipulation mathematically, we realized that we are having a condition that is called orthogonality condition, with different two modes, with one condition that omega n does not equal to omega m. I hope by the end of this video that you have understood what I have explained today, and next video is going to be related to the normalization of mode shapes. Thank you, and see you in the next video.